Yeah, in the previous videos we discussed how BatchNorm works. Let's now discuss why BatchNorm works. I can't give you the definitive answer here, but at least I pulled together some theories and some practical or empirical evidence to kind of support certain claims. So I think that might be interesting if you are really interested in studying BatchNorm. So originally, the paper that proposed BatchNorm mentioned this internal covariate shift. So the authors of the original BatchNorm paper said that batch normalization accelerates training by reducing this internal covariate shift. What is this internal covariate shift? What does it mean? So it's essentially saying that the layer input distribution changes. So there's a shift in the distribution of these inputs to a given layer. So it's essentially a feature shift. So the features, if you think of the inputs to a given layer as the features, the distribution of these features shift over time during the course of training. So that's one theory that happens during a regular training, and BatchNorm helps preventing it by renormalizing these inputs. However, there's no guarantee for that, and there's also no strong evidence for this theory. I will show you a paper that kind of debunks this theory. Another theory that's like more what I'm kind of sometimes speculating is that BatchNorm provides additional parameters that might help. However, I think this is also maybe not a reasonable theory because it is something you can simply test by inserting or making the previous layer a little bit larger, adding some parameters to it. And I think at least someone would have tested that already, so that's probably not the case. Another idea is maybe that it makes these layers a little bit more independent of each other. So for instance, if you think about one layer producing some nonsense outputs or something, is very... So let's say you have a late layer in the network, layer very close to the output. It kind of depends on the previous layers of giving it good input. So if you screw up one of the early layers, well, then the output layer or all the other layers are really also depending on that. So you are it's like a domino effect. You have like, if you screw up one layer, you screw up the other layers too. And the same thing can happen during both the forward and the backward pass, right? Because in the forward pass, you go from the left to the right, and in the backward pass, you go from the right to the left. So that way, if something is wrong in one given layer, it will affect all the other layers. And maybe with this BatchNorm, this kind of helps decoupling the layers a little bit in terms of if one layer screws up, the other layers are a little bit more robust to that. But it's also just one of the many theories. So here I found a paper from 2019. I mean, it might already be outdated, I don't know. But I found it interesting, so I included it here. So this paper is called How Does Batch Normalization Help Optimization? So here they, in the abstract, basically state that BatchNorm is good for stabilizing the training, but also the exact reasons are still poorly understood. And then they mention the internal covariate shift as one of the potential reasons, but they demonstrate that such a distributional shift or distributional stability of the layers has little to do with the success of BatchNorm. So they are essentially saying the covariate shift or preventing covariate shift is not really why BatchNorm works so well. Instead what they find is that it makes the optimization landscape significantly smoother, so essentially creating a smoother loss surface. And this helps then with making the training more stable, and it allows us to have larger learning rates and have faster training because we have more stable behavior of the gradients. So I took some visualizations from the paper shown here. I don't want to go into too much detail about this paper. I mean, if you're interested, you're very welcome to read it. So here are only a few takeaways. So what they say is essentially that BatchNorm enables faster convergence by allowing larger learning rates. I found that interesting. So let's focus on the left plot first. That's the training accuracy here. And this is the number of steps. So instead of epochs, they have steps here. So that's the steps. You can think of it as iterations or mini batch updates. Doesn't really matter whether we have epochs here or mini batches plotted. It really just represents the training, the course of the training. So we have 15,000 updates. And you can see there are 4 graphs. So the red ones are a standard network with learning rate 0.1 and 0.5. And just looking, let's use the red for this one. So just looking at this red curve here, you can see the 0.1 trains relatively well. It reaches 100% at some point. However, the large one, the 0.5, doesn't train so well. So so the learning rate is essentially too large. So what we have then is the same 0.1 and 0.5 now with batch norm. Now if you look at it, the one with 0.1 trains actually faster. Also with 0.5 it also trains at all. I mean, the other one with 0.5, when we had the standard one, it fell apart here, right? So batch norm essentially allows us to also have larger learning rates. In this case, the larger learning rate is not better than the 0.1 learning rate, but it is stable. It is training. What the interesting takeaway here is, though, is that overall the training with batch norm is faster. So even though we reach the same performance in the end in the training set, what is nice here is that batch norm trains faster. Now on the right hand side, that's what we really care about. That's the test accuracy. How does the test accuracy look like? So here I assume they are testing, or they're using the same test set so they train the model and then they use the same test set to make this plot where this is really like the training steps here. So what we can see here is during training. So first, also again with batch norm, we see that the accuracy increases faster. In the end, I would say there's a little difference between the red and the blue one. There's a slight difference, so you can say maybe batch norm performs better. And you can see also batch norm is stable with a 0.5 learning rate. I wouldn't say that training is faster or convergence is faster because it allows us larger learning rates, because we can see the smaller learning rate still works better. But what I would say is it's making our training more robust. So it's maybe requiring less time to find good hyperparameter settings to get good results, which is kind of nice. So if it just stabilizes training, this is something I would always want to do, right? Why would we not want batch norm then? All right, so next they looked also into this covariate shift here. Let me take a look at this figure to refresh my memory here. Yes, so what they are showing here is, again, training, the course of the training and the training set accuracy. And on the right-hand side, these are the distributions of the activations in the different layers. So they look at layer 2, layer 9, and layer 13 of a deep neural network, a VGG network. We will talk about VGG in the convolutional network lecture. So what we can see is for standard that the distributions across layers are slightly different. So I can't really read these numbers here, it's very small, but these should be ordered by increasing size. So I think this corresponds here to the steps. So the steps that we see here. So this at the bottom is the later training, and you can think of each bell curve or each histogram here as the activation, the distribution of the activations at that given step. So what you can see is they are all kind of in line here. So there's not much distributional shift. I would say here maybe there's some shift. You can see it's maybe, I'm not sure, it's hard to see, that the mean of the distribution during the course of the training, during the steps, shifts a little bit to the left, for instance. But we can also see this a little bit here, right? So in that way, this one is the one with batch norm. It's not, I would say, that much different. Now what they did is they produced a batch norm variant by adding noise to it. So here you can clearly see that the distribution shifts. So you can see here this peak is very different from this peak. So you can see a huge shift of the distribution. So here this one. However, when they then do the training, so you can see here on the left hand side when they do the training, both the the batch norm and the noisy batch norm both perform really well. So even though there is covariate shift or there is no covariate shift, it doesn't seem like it affects the performance that much. So even let's say if batch norm fixes this covariate shift, they think it's not really the explanation why it results in such a good performance, because then you would expect for this case here a very poor performance, but that's not the case. So that's just one observation from this paper here. Okay, now let me list a few more papers. I don't want to go into these in too much detail, but if you are interested, you are encouraged to read more. It's of course not required for this class, but if you're really interested in batch norm, doesn't hurt to read those. Okay, so just in chronological order, there is the theory that it reduces covariate shift. So this is the original paper. Then we just saw the paper that says that it makes the optimization landscape smoother. There's another paper I found where they say that the reason why batch norm works so well is that batch normalization implicitly discourages single direction reliance. Then another paper from 2018 also says that it acts as an implicit regularizer, and that is then helping with the generalization accuracy. And another paper was not so positive about batch norm. It says essentially that batch norm causes exploding gradients. So we will actually talk about these skip connections in a future lecture too, by the way. Let's get now to the practical advice section of this video. So there are also slight modifications of batch norm. So one is putting batch norm before the activation. So this is the original version of batch norm that was discussed on the previous slides or previous video and also presented in the original paper. So here the workflow is as follows. First we compute the net inputs, and then we apply batch norm, then we apply the activation function, and then we compute the next layer inputs. However, we can also put batch norm after the activation. So what we do is we essentially flip the order here. We first apply the activation function and then use batch norm. So we can see at net inputs, applying activation function, batch norm, and then computing the next layer inputs. This could make more sense in practice if you think about it as, let's say for simplification, let's say you use batch norm and batch norm learns to standardize your feature or activation distribution, let's say at mean 0, right? So you have now 0 mean features, but then you apply the activation function. Let's say on the left hand side we apply the activation function, then it would kind of change this distribution before it gets to the next layer, right? Because let's say we have mean 0 for a given feature, and if you use, for example, a logistic sigmoid function, then the mean will change from 0 to 0.5, right? So the next layer receives inputs that are centered at 0.5 and not centered at 0, right? So in that way, the sigmoid would remove also the negative values. So in that way, maybe it makes more sense to put batch norm after the activation. Personally, I haven't found any big difference. I haven't benchmarked this extensively. I tried it here and there. I didn't notice a big difference. I did some searching online. There was a repository that I found where they did some experiments, multiple ones, and found that before and after did make or have a difference. And they found, for instance, that putting batch norm after the activation indeed resulted in a better accuracy. So, I mean, why not? It may make sense just to put it always after the activation and not worry about it. All right, some more practical consideration. So batch norm, I should also say, only works really well if we have reasonable batch sizes. So if we make the batch sizes too small, then batch norm doesn't work very well anymore. So that might be explained by the fact that these mean and standard deviation statistics become very noisy if we have small batch sizes, right? So here I found a paper. This is actually a paper about an alternative to batch norm. It's more for convolutional networks, but it's called group norm. We can revisit this maybe later. We don't have to talk about group norm here. It's really just something that doesn't work for multi-layer perceptrons. It's only for convolutional networks. But what I found interesting was here this figure. Ignoring the group norm plot here, what you can see is they did an experiment with different batch sizes, and here's the percent error. And they have it here at 32. Unfortunately, they are not showing larger ones, but you can see 16 and 32 both work, but if you make it smaller, so if you make the batch size smaller, like 8, 4, or 2, then batch norm becomes really bad, so you get a very large error here. So just a practical consideration, if you use batch norm, it's highly recommended to use a batch size greater than 16. In practice, I would even say bigger than 32 or even 64. So here's some further reading resources if the previous ones were not enough, if you are interested. Like I said, we can't cover everything in this course. This is an introductory course, so I have to be very selective with topics. But if you are interested, some additional papers that you might find interesting, maybe in the context of your project, you can try one or the other paper and see whether that helps. So one is conditional batch norm, which is essentially including class information. So having different parameters for the different classes in a dataset, which kind of makes sense. Then there's a paper on measuring the effects of data parallelism on neural network training. So here, what I just found interesting is it's not directly related to batch norm, but it's related to the previous slide regarding the batch sizes. So sometimes in practice, people say, don't use a large batch size. So let's go back. So there are two theories. One theory, or one, not theory, but a recommendation is to use large batch sizes, because large batch sizes help you to utilize the GPU better, because you have larger matrix multiplications, and then the training will be faster and it's better. Some people say choosing smaller batch sizes is better because it helps with generalization, because then maybe the loss gets we are less likely to get trapped in local minima on the loss surface. However, this is very controversial. Here was just a paper I found interesting where they say basically that they don't find any evidence that large batch sizes degrade the performance. And then another one here is an alternative to batch normalization that I have not tried it myself, but it sounded interesting. It just came out this year. I saw that this year. I haven't even read this yet because I have such a huge list of papers I find interesting and I want to read, but there's only so many hours in the day. But that sounded pretty appealing. So they say that they present a plug-in replacement for batch normalization called exponential moving average normalization, which improves the performance of existing student-teacher based self and semi-supervised learning techniques. I'm not sure whether it applies also to regular networks, but could be worthwhile looking into. So I just had that on my reading list and I thought I'd just include it here. And the last one I have here is it's actually without batch normalization. So usually people say batch normalization is really important to reach good performance. And here in this recent paper, also from 2021, they demonstrated that also you can actually get good performance without batch normalization. So they mentioned that previous work was already successful in demonstrating that you can train without batch normalization and get good performance, but these models do not match the test accuracies of the best normalized networks and are often unstable for large learning rates or strong data augmentation. So while it is possible to get good performance, it's not as good as with batch normalization, and the models are more unstable. But in this work, they have an alternative to make them stable, so they call that adaptive gradient clipping. So gradient clipping is a technique that if you have a very large gradient, you clip it at a certain value so that it doesn't cause problems like exploding gradient problems. And they say by having an adaptive version of that gradient clipping, they can train a network without batch normalization and get a good performance. But yeah, again, this is a very recent paper. Time has to tell whether this is really also working well across other architectures, but that might be also something cool to look into, maybe in the context of your class project. So again, I'm just throwing out some ideas or interesting reading material here. You don't have to read that, of course. I'm just sharing it because it sounds interesting. All right, so one last thing. I mentioned here these batch sizes, and you may have noticed they are all powers of 2, right? 2 to the power of 2, 3, 4, 5, 6, and so forth. So why is that? Why do people usually choose batch sizes in powers of 2? So that has something to do with how GPUs work. There's this, just briefly, there's this paradigm, single instruction, multiple data. So it's like you have a multiple data points, or let's say multiple values in a vector, and you have a single instruction, let's say like addition, and you can distribute this instruction to apply it to everything in a vector. So that's like how on a certain level parallelism works on a CPU and GPU. So, and on GPUs, the number of processing cores is usually a power of 2. That's just how, the chip design works. Now, you can take that and take it or make it an advantage by choosing a batch size that is also a power of 2, because then you can better balance out how these cores are used. For instance, if you have 32 columns in a matrix, you can, so let's say you have your design matrix, you would do a transpose on this matrix, and then these columns, you can map them to dot products to each of the processing core. So if you have 16 processing cores, for instance, you can run 2 dot products on these 16 cores, right? So if you have only 31 columns, then one core would be finished faster, but it has to wait until the other ones finish anyway, so you don't fully utilize your GPU. So in this case, it's just so that the GPU is better utilized. People prefer these powers of 2 when choosing batch sizes. But this is also anecdotal. You don't have to, of course, choose batch sizes that are powers of 2. It's just, you know what it is? It's actually also making life simpler, because there are so many hyperparameters to tune and to consider. And if you also would consider values between values powers of 2, then you would even have more hyperparameters to consider, right? So if you say I only tune powers of 2, so you have 32 batch size, 64, 128, and so forth, then this is less than saying I will consider 25, 30, 35, 40, and so forth, right? So in this way, it's also one way to keep things simpler for hyperparameter tuning. And of course, it utilizes the CPU and GPU better, but in practice, it doesn't make such a huge difference. It's not like you get any significant speed up through that. Okay, so that was enough about batch norm. Let's now talk also about weight initialization.